Salutations, mini mathematicians. We're going to be continuing solving systems of equations. Last time we solved systems with graphing, and we saw that if your point of intersection is not integers, then we have a really hard time solving with graphing. So today we're going to learn one way of solving algebraically, and it's solving systems with substitution. So our purpose is to be able to isolate one variable and substitute it into a second equation to create one equation with one unknown. And you know how to solve one equation with one unknown. You've been doing it for years. We're going to solve and then substitute into the first equation to create one equation with one unknown. Solve and write your solution as an ordered pair. Because remember, we have to solve for both variables. And our answer is an ordered pair, or it's going to be infinitely many solutions or no solutions. One ordered pair if the system intersects once, different slopes. No solution if the system intersects nowhere, parallel lines, and infinitely many solutions if the system is indeed the same line. Cool, let's get started. Substitution method for solving systems of equations. Directions: find the value of each shape. Well, if we look at this shape, we see that star star circle is 13. So we're going to substitute in for star star circle to be 13. So here we have a star star circle, and here we have star star circle. So this is equal to 13. Now our top equation is one equation with only one variable, circle. So what we have here is 13 plus 2 circles is equal to 19. Well, then we know that 2 circles, and I like to fill in my circle so it doesn't look like a 0, is equal to 19 minus 13, which is going to be 6, which means one circle is equal to 3. Now that you know one circle is equal to 3, we can substitute that value into the other equation. And now we have one equation with only one unknown, star. Star star plus 3 is equal to 13. So we know that 2 stars would be equal to 10. So 1 star has to be equal to 5. So we're going to explain in words how we determine the value of each shape. We only have to explain in words for this one, and then we can just figure out the other ones. So what did we see first? I saw that star plus circle was equal to 13. And we do want to put that plus there because we're adding these terms, not multiplying them. I saw that star star circle equals 13 and substituted in 13 for star star circle in the top equation. Now I guess it would be then, because now is like present tense, then is past tense. Then I had one equation with one unknown, circle, and solved for circle. Then I used the second equation to substitute in the value for circle to make one equation with one unknown. In this case, the one unknown was star. Next, I solve for star. Cool, great job. Okay, I would like you to look at 2 and 3 on your own and see if you can figure out what the square and circle are and then what the square and star are. Pause the video and we'll go over it in just a second. Okay, let's see how we did. For number 2, I found the square to be equal to 12 and the circle to be equal to 6. The first thing I saw was that one square is equal to 2 circles, so I could substitute in each square being 2 circles. Then I had 1, 2, 3, 4, 5 circles equaling 30, so I knew one circle was equal to 6. Then I needed to use the second equation, the bottom equation, and I substituted in circle to be 6, and 2 circles would be 12, which is equal to my square. The third one is a little bit different. When I look at the third one, there's infinitely many possible solutions we can have here. We could have square to be 10 and star to be 1. We could have square to be 9 and star to be 3. We could have square to be 8 and star to be 5, or each of them could be 7, and so on. So how does this solution to the problem differ from the previous ones? Well, for number 3, there's infinitely many solutions because the second equation is a multiple of the first equation. Because if I took the first equation and multiplied it by 2, notice 2 squares become 4 squares, and 1 star becomes 2 stars, and 21 times 2 is 42. And we know when equations are multiples of each other, they're actually the same equation. So we're going to have infinitely many solutions when graphed these two lines are the same line. So then it says using shapes create another system that would have the same solution. So I wanted to make another system that's going to have infinitely many solutions. So one option I thought of was triangle plus square is 13. And then I multiplied everything by 2. So instead of 2 triangles, I'm going to have adding 6 triangles. Sorry, I multiplied everything by 3. I misspoke here. So instead of 2 triangles, I'm going to have 6. 1, 2, 3, 4, 5, 6. And instead of 1, but if I multiplied everything by 3, this shouldn't be 26, should it? No, it shouldn't. It should be 39. Perfect. So multiplying everything by 3 on both sides, 2 triangles become 6 triangles, 1 square becomes 3 squares, and 13 becomes 39. So whatever system you made, it just needs to be a multiple of each other, and we should be using shapes that we're adding together. Great job. Problem number 4. It says problems 1 through 3 use shapes to represent systems of linear equations where each shape represents a different variable. So here it says if x is equal to triangle, and I like putting my x's on the triangle just so I don't mess this up, and y is equal to circle, so I'm going to put y's on my circle. Write a system of linear equations that represents the situation to the right. Okay, so I'm going to label these 1 and 2. And if I look at 1, if I have x plus x plus x, that gets me 3 x's. And if I have 1y is equal to 8, and equation 2, I have 1x, and then I have 3y's is equal to 40. Now, the next part says, what is the value of x and y? Explain your process and solve and show all your work. Okay, so because we want the reader to be able to follow our work, what we're isolating, what we're substituting into, we're going to use a t-table. And what we're going to do is I'm going to isolate y. So I'm going to use our t-table. I'm going to write equation 1 on this side, 3x plus y is equal to 8, and equation 2 on this side, x plus 3y is equal to 40. This is important because we want to make sure we're using both equations to solve the system, not the same equation twice. If you use the same equation twice, you're always going to end up with infinitely many solutions, so this helps you avoid that mistake. So like I said, we're going to isolate y because y looks very simple to isolate here. Its coefficient is 1, so we're going to subtract 3x from both sides, and we get y is equal to negative 3x plus 8. Now this is like a dance. We're going to isolate, substitute, isolate, plug in. So what we have here is we know that y is equal to negative 3x plus 8. So we're using the other equation and substituting that in for y. Y is negative 3x plus 8. And we're just going to write everything else around it. Gee golly, now we only have one equation with one unknown. Yay, we know how to solve this, you guys. Okay, so let's simplify this. So we're going to distribute the 3. So we'd have x minus 9x plus 24 is equal to 40. I'm going to combine my like terms. So x minus 9x is negative 8x. I'm going to subtract 24 from both sides, and I get 16. Divide both sides by negative 8, and x is equal to negative 2. So that's great, but remember our answer is an ordered pair, so we only have part of our answer. So from here, we're going to substitute back into our first equation. Remember, isolate, plug in, isolate, plug in. It's a dance. So now our x is negative 2. So y is equal to negative 3 times negative 2 plus 8. We're just going to use order of operations. Negative 3 times negative 2 is positive 6. And 6 plus 8 is 14. And then we're going to put it all together for our final answer is an ordered pair. And we're going to give it some flair. Remember, an ordered pair x comma y is just in alphabetical order. Super fancy. So C says, what if you solve the second equation for x and substituted that value into the first equation? Do you think you'd get the same values for x and y as we did above? Well, let's take a look at this. We're going to isolate x. So we're going to write our two equations, and we're going to have equation 2 on this side just because that's the one we're going to be using first. Equation 1 on this side, 3x plus y is equal to 8. So when you're taking a look at the system, notice in equation 2, x also has a coefficient of 1. So it's going to be very efficient to isolate x in equation 2 because all I have to do is subtract 3y from both sides. So I'd have x is equal to negative 3y plus 40. Now, this is the value for x, so I'm going to substitute it in for x in the equation I have not used yet. And again, remember, it's really important to keep our work organized because we need to make sure to use both equations to solve the whole system. Yay, we have one equation with only one variable. We can solve this. Okay, so when I distribute through, I'm going to have negative 9y plus 120 plus y is equal to 8. Negative 9y plus y is negative 8y. I'm going to subtract 120 from both sides and get negative 112. Divide both sides by negative 8, and we get y to be positive 14. Same. So now you know what to do. We isolated, plugged in, isolated, plugged in. Or in this case, because the name of the method, it's called substitution. Isolate, substitute, isolate, substitute. So we're going to go back over here. My y value is 14. So now we have x equals negative 3 times 14 plus 40. X equals negative 3 times 14 is negative 42 plus 40. X is negative 2. Are we surprised? No, because that's what we got over there. But you're not done yet. Remember your last step. Write your answer as an ordered pair and give it some flair. Groovy. Okay, so would you get the same values for x and y as you did above? Justify your answer. Yes. The solution to the system is the point of intersection. And the system didn't change. The system stayed the same? Yeah, system stayed the same. Point of intersection doesn't change, solution doesn't change. And what's really important about this is it does not matter if you isolate x or y in equation 1 or 2 to begin substitution. I need you to work smart, not hard. And when I say work smart, not hard, obviously I could have isolated y in equation 2, but then you're dealing with a third of an x and 40 thirds. That's gross. That's going to lead you to mistakes. Ew, nasty. Obviously, I could have isolated x in equation 1, but then you're dealing with a third of a y and 8 thirds. Blech, yuck. Don't do that to yourselves. The other thing I want to remind you is that when we write our solution as an ordered pair, it's an alphabetical order, x comma y. And in some cases, if I change the variables like a and b, it would be a comma b because we're doing that in alphabetical order. Cool. Okay, so let's take a look at number 5 and 6. So it says the method used in problem number 4 is the substitution method. So this is important, so I'm going to give it a circle. Substitution method for solving a system of equations. With substitution, one equation is solved for one variable, then that solution is substituted into the other equation to solve for the second variable. And we like to use a t-table to keep things nice and organized. And remember, our goal here is to create one equation with only one variable. Because you know how to solve that. Okay, so 5 says write a system of equations for the picture and solve using substitution method. Solve, show all your work, and verify your solution. So we are going to let square equal x and let circle equal y. And so here, if square is x, we're going to just put x's in the squares. And then I'm going to put y's in the circle because that helps me out a lot because I'm such a visual person. So from there, I am going to label these as equation 1 and 2. So equation 1 is going to be 2x plus 7 is equal to y. And equation 2 is going to be 3x plus 2y is equal to 35. So looking here, is there one variable that's more efficient to isolate or already isolated? You got it. Equation 1 already has y isolated. So I'm going to write my t-table, and I'll put equation 1 up here, 2x plus 7 equals y. And I'll put equation 2 on the right, 3x plus 2y equals 35. And this way I just won't forget to use both my equations. So equation 1 already has y isolated, so y is equal to 2x plus 7. I'm going to take that value, I'm going to substitute it in for y over here. 2x plus 7 is my y value, and then I'm just going to bring everything else down. And yay, we have only one equation with just one variable x. Yes, we can solve this. So from here, we're going to solve this. We are going to distribute the 2, 4x plus 14. We're going to combine like terms. We're going to subtract 14 from both sides. and divide both sides by 7, and x is equal to 3. But remember, we're not done yet. We still need to substitute into the other side to solve for y. So now my x value is 3. I'm going to bring everything else down, use order of operations, multiply, and then add. I get y to be 13. And your final step, you guessed it, write your answer as an ordered pair and give it some flair. Wonderful. Great job, mini mathematicians. Okay, so for our next system, what we're going to do is we're going to let circle equal x, and we're going to let y be our triangle. Let our triangle equal y. Okay, so why don't you go ahead and finish 6, and we'll go over the answer together. Pause the video, and we'll go over number 6 when you're done. Okay, taking a look at number 6, first thing you need to make sure you have written correctly is the system. So we have 3x plus 5 is y, and 3x plus 3 equals y. You might be already thinking, equal x's and equal y's with different constant terms. I'm thinking that these are going to be parallel lines that never intersect, and you are correct. Notice you can isolate y in either of them because they're already isolated, and I'll substitute y into the other equation. When you subtract 3x from both sides, you get a false statement. What does that tell you if you get a false statement? That means there's no solution. These lines are parallel and never intersect. Remember, that is the symbol for parallel lines. Okay, so the next set of problems, we are asked to solve each system using the substitution method and showing all of our work. If you don't have enough room to show your t-table, you can always use your notebook or the back of a page. So if I didn't have enough room to solve 7, maybe I would use the back of my last page I was working with, and I would write number 7 and just start my t-table there. I really don't like squishing my numbers, because if I have to squish my work into a little space, that's how I oftentimes will make mistakes. So I'm just going to use the back of my paper on number 4 so I can show all my work. So I'll label these as 1 and 2, and I notice that y is already isolated in equation 2, so I'm going to write equation 2 first. 2x plus 3 equals y, and equation 1 on this side, 3x minus y equals negative 1. Notice I'm taking the least steps to be most efficient in my process. So from here, I know that y is equal to 2x plus 3. I'm going to substitute that in for y over here. 2x plus 3. 3x, notice this is a minus. It's really a negative 1 that's being distributed. I'm going to distribute that negative 1, so 3x minus 2x minus 3 is equal to negative 1. 3x minus 2x just gets me x. I'm going to add 3 to both sides, and I get x is equal to 2. Remember, though, you're not done yet. Your answer is an ordered pair, or no solution, or infinitely many solutions. So from here, I know my x value is 2. So I know that y is equal to 2 times 2 plus 3, order of operations, multiply first, then add, and y is equal to 7. But we're not done yet. You have to write your answer as an ordered pair and give it some flair. And if you're doing it like this for your homework, if there's not enough room on the printed paper, you can always just say see work, and you can scan in this work attached at the end. Awesome. Okay, why don't you go ahead and do 8, and we'll go over it in just a second. Let's see how you did on number 8. Number 8, I labeled these equation 1 and equation 2. Should look more like a 1. And I noticed that in equation 2, x had a coefficient of 1, so it's going to be really efficient to isolate x by just subtracting 6y from both sides. So now I have x by itself, I'm going to substitute it into the equation I have not used yet. And when I solve for y, because I only have one equation with one unknown, yay! I get y is 4, but I'm not done yet. Then I need to go back over and substitute 4 for y into my first equation to get my x value of -6, and then write my answer as an ordered pair and give it some flair. Give it some flair. Cool, great job, mini mathematicians. Substitution method sure is a lot of fun. So we have 9 through 14 to finish. It's all substitution method. What I'm going to help you with is I'm going to look at 10, 12, and 14 with you, and then you're going to do the other ones on your own. So taking a look at number 10, of course, I'm going to label these as 1 and 2. And again, if you feel like you need more room, feel free to show your work on a separate piece of paper, labeling this as number 10. So here I notice I have a fraction and I'm kind of seeing some similarities here. So what I'm going to do is I'm going to multiply all of equation 2 by 2 and see what I get. I get 3c plus 4d is equal to 22. So I notice equation 1, 3c plus 4d is equal to 7. I notice they're really same. We have 3c plus 4d on both sides, and we have just a different constant term. So I'm really thinking that this is going to be parallel lines with no solution. But let's continue just to make sure we have that correct. So I see that these are both going to give me some nasty fractions. So I'm just going to deal with equation 1, which is 3c plus 4d is equal to 7, and then equation 2. And I am going to use the non-fraction amount for equation 2. I'm going to use 3c plus 4d equals 22. From here, I'm going to isolate c, so I'm going to subtract 4d from both sides. I get 3c equals -4d plus 7. I'm going to divide every single term by 3, and I'll get c equals -4/3 d plus 7/3. So, like I've said before, what I'm going to be doing is now take this value for c and substitute it in for c into the equation I have not used yet. So -4/3 d plus 7/3. And I'm really happy because I'm multiplying all of that by 3 and I'm going to get rid of my fractions. Yes. Okay. Plus 4d is equal to 22. Okay, when I multiply through, I end up with -4d plus 7 plus 4d is equal to 22. The variables cancel. I get 7 equals 22, which is a false statement. So because this is false, what do we know about the solution? This is no solution because we have parallel lines. Remember, that's the symbol for parallel. And I do want to make sure people know that my solution is no solution. So I'm going to give it a little bit of flair. Awesome. Okay, let's take a look at the next one, number 12. I said I'd do with you. So number 12, very similar. I'm noticing I have this fraction, and you can always use your multiplicative property of equality, which tells you you can multiply both sides by the same number, and the equation will still be true. So what I'm going to do here is I'm going to take equation 1 and multiply both sides by 2. When I do that, I get 5x plus 2y is equal to 8. Gee golly, is this deja vu? Look at equation 2. Equation 2 is also 5x plus 2y is equal to 8. So in fact, these lines are the same lines, so we have infinitely many solutions. Infinitely many solutions. And if you went and solved using substitution, you would end up with a true statement. And I'll show that to you really quickly. I'm going to use equation 1, 5x plus 2y equals 8, and equation 2, 5x plus 2y equals 8. I'm going to isolate y since 8 is divisible by 2. And I'll have 2y is equal to negative 5x plus 8. And then when I divide by 2, y is equal to negative 5 halves x plus 4. So then when I substitute that into the other side, and again, you don't have to show this work if you already saw it was infinitely many solutions because you manipulated them to rewrite them as the same equation. But what we can see is 5x plus 2 times negative 5 halves x plus 4 is equal to 8. So 5x, when I multiply by 2, I'm going to actually clear that fraction, which is really great. Negative 5x plus 8. These variables cancel out, and I get 8 equals 8, which is true. It's a true statement, but it doesn't allow me to substitute into the other equation to solve for a point of intersection. So these two lines are actually the same line. They intersect everywhere, therefore infinitely many solutions. Cool. 14 was the last one I said that I would do with you. So taking a look at 14, don't be scared by the fractions because it looks like we're going to be able to clear them pretty easily. So I'm going to multiply equation 1 by 2. And when I do that, I get h plus 2k is equal to 1. And then I'm going to multiply equation 2 by 7. And that gets me h plus 7 is equal to 4k. So here you have an option. I could isolate h in equation 1 or h in equation 2. They're both going to be pretty efficient to isolate here. So I'm going to write equation 1 and equation 2. H plus 2k is equal to 1. And h plus 7 is equal to 4k. And I'm going to decide to isolate h here by subtracting 2k from both sides. So h is equal to negative 2k plus 1. I'm going to take that value and substitute it in for h on the other side, leaving me with one equation with only one unknown. Plus 7 is equal to 4k. I'm going to add 2k on both sides to bring my variables to the same side. So I have 1 plus 7 is equal to 6k. 8 is equal to 6k. Divide both sides by 8, and you have k is equal to 6 over 8, which means k is equal to 4/3. But remember, we're not done yet. We're going to need to substitute my k value. So h is equal to negative 2 times my k value, which is 4/3 plus 1. 2 times 4 is 8, and it's negative. So we have negative 8/3 plus. I really like rewriting this one as a fraction so I can not make silly mistakes. This is 3/3. And negative 8 plus 3 gets you negative 5. So negative 5/3. And final step, write your answer as an ordered pair alphabetical order and give it some flair. So if you think A, B, C, D, E, F, G, H, I, J, K, so this is H, comma, K. So negative 5/3, comma, 4/3. And you can always verify by substituting those values back into the originals to make sure you have a true statement. The point lies on both the lines, making that the only point of intersection. This would be impossible to solve using graphing by hand. Okay, so let's take a look. You're going to finish 9, 11, and 13. You're going to finish 9, 11, and 13. Pause the video, and we're going to go over them in a second. Okay, let's take a look at number 9. When I'm looking at 9, and again, if you need more room, please show your work on another piece of paper. When I'm looking at 9 here, I see that y in equation 1 is more efficient to isolate because it has a coefficient of 1. And then I'll substitute that into equation 2, and when I solve for x, I get negative 1. Then I substitute that back into my equation with y isolated to get y as -8. I write my answer as an ordered pair, -1, -8. For system number 11, taking a look at system number 11, you could isolate A or B in equation 1 or B in equation 2. They all are going to be efficient to isolate. I decided to isolate A in equation 1 to get -B plus 6. Please be careful with your 6's and your B's. They can look very similar. So from here, I substituted that value in for A. I find it really helpful to circle or draw arrows into this variable I'm substituting into so I don't make a silly mistake. And then always double check that you have one equation with one variable. I got B to be 3/2, and when I substituted that back in to A, and notice that's a -B, so it's -3/2, plus 6, I get 9/2. And we do want to write these as improper fractions. Awesome. And then 13, the last one you needed to do, we had R and S. S was already isolated, so I didn't take the time to clear my fractions. And then I substituted that value in for S in equation 2, and I solved for R to get -1/3. From there, I substituted back in to my equation where S is isolated. I got S to be -1/4 and wrote my answer as an ordered pair. And if you need to sing the ABCs to know that it goes R, S, be my guest. I have to do the same thing. And that is our ordered pair with some flair, our point of intersection. Again, this would be very difficult to solve graphically. So let's take a look at 15. 15 and 16, you're going to see similar problems like these on your dots, on your exams, on your homework. So remember, we're looking at systems of equations. We're looking at systems of equations that are two equations. So what we want to look here is it says find the point of the graph of x plus 2y equals 6. So that's our first equation in the system, where the y value is equal to the x value. And this is our second equation in the system. So where it says the y value is equal to the x value, that means their equation is y equals x. And if we want to find the point of intersection where they're equal to it, that means we are just solving our system. So from here, I'm going to write my system. So equation 1 is x plus 2y is equal to 6. And equation 2 is y equals x. And we can just solve that using substitution. I'm going to write y equals x on first because the y value or the x value is already isolated. And equation 1 is x plus 2y equals 6. So here we have y is equal to x. So I'm going to substitute this value in for the y. And we have x plus 2x is equal to 6, 3x is equal to 6, so x is equal to 2. Coming back up here, y is equal to 2. Write our answer as an ordered pair and give it some flair. So 16 is the same, where I'm giving you the first equation of my system algebraically, and I'm giving the second equation in my system verbally. Remember, is means equals. Go ahead and finish solving 16. Pause the video, and then we'll go over it together. Okay, on 16, we should have gotten the answer 9, 7. And you can see my work. I noticed that the y's are both isolated, so I just substituted in equation 1 into equation 2, and I had one equation just with x's. When I solved for x, I got x to be 9, and then I substituted that back in to find y to be 7, and wrote my answer as an ordered pair with some flair. Great job, mini mathematicians. Keep up the excellent work. You are doing fabulous. This is when we really start to be doing like mathy math. Like, this is impressive stuff. If you look back through your notes right now, what you were able to do today. Excellent job.